projects, and she is a very eminent teacher. Today, she is going to take a class of subject carbohydrate. I hope this subject will be very crucial, and this month is very crucial for all the GPAT aspirants. So I request all the participants to uh, observe very closely, determined, so that you will be get benefit out of this class. Now I request Dr. B. Geetha to unmute. Madam, over to you. So without much ado, now I request Dr. B.
Okay,
Geetha
sir.
to
Okay,
take the
sir.
session. Thank you, ma'am.
Okay, sir. Happy morning to one and all present over here. Am I audible?
Yes, madam. Yes, ma'am.
Okay. Thank you, one and all. Thank you, one and all present over here. I take this opportunity, and first of all, I would like to submit my pranams to Lakshmi Saraswati, and who is there with us for all our studies, and may her blessings shower on all of us today morning. And I take this opportunity to thank Pharmacy Alumni Association, Madurai Medical College, Madurai, and Indian Pharmaceutical Graduate Association for their beautiful opportunity given. And I hope I will do my level best with this topic. And I also thank all the team members of Abhirami College of Pharmacy, Sri Abhirami College of Pharmacy, the management, the principal, and all the staff members who constantly encourage me in all these professional activities. With this thanking note, I am going to start my topic, carbohydrates. If there is any audibility problem, kindly let me know this. So carbohydrates, so they are compounds which comes under the normal phytoconstituents, which is a primary metabolite which is present in the plant sources. So the carbohydrates are the hydrates of carbon. The carbohydrates are polyhydroxy aldehydes or polyhydroxy ketones. That means we have more number of hydroxyl groups. If we have more number of hydroxyl groups, that particular component comes under the polar category. So when we take the solubility of carbohydrates, it is freely soluble in water. So these carbohydrates are freely soluble. Whatever we are taking daily, our rice, idli, like wherever we are taking coffee, we are adding sugar. Everywhere we are having in one or other form carbohydrates. So when we take these carbohydrates as a primary metabolite, initially we were seeing like this, they are acting as the energy giving, or we have studied in our biochemistry. These are the sources of our energy. So intake of carbohydrates biochemically is essential for every human's life.
I'm sorry to
So
disturb you, ma'am.
yes, sir.
Ma'am, your slide is not moving. It is on in the first slide only.
Okay, sir. 1 second, sir. So thank you, sir. So the carbohydrates are the compounds which are having all this biological importance. They provide energy. They are the cell components. They form the part of the cells and tissues as in one or other form, like cellulose. We have heard about cellulose, which is a polysaccharide which is present in the cell wall. And the cellulose are rich in fiber containing plant materials, and which we are taking as a dietary supplement. So coming to this carbohydrates, as I said earlier, these are the sources. They are enriched with our foods, like they are found in our foods, whatever we are taking, like rice, breads, and sweets, sugarcane, etc. So these are some of the classification. Coming to the chemistry part of the carbohydrates, they are polyhydroxyaldehydes or ketones. So they are divided broadly as saccharides means, and it is taken from the word Greek, it means sugar and water soluble. So the word saccharide means it is taken from the Greek word, which means sugar. So they are divided into monosaccharides, disaccharides, oligosaccharides, polysaccharides in general, based on the number of glucose units present in it. The monosaccharides are simple units like glucose, fructose, mannose, galactose, etc. And the disaccharides, they are combined form of two monosaccharides. In oligosaccharides, it is 3 to 10 monosaccharide units. The example is raffinose. Polysaccharides, it contains more numbers like hundreds or thousands, and they are again divided into plant sources and animal sources. So if we take the plant sources, it is starch, glycogen, and cellulose, and in case of animal sources and then fungal, it is chitin. We have heard like it is a very jelly-like substance. So the polysaccharides are present like it's a long chain, and we are talking about the linkages. Coming to the GPAT point of view, we may get a question like, what are the functional units of monosaccharides? So it is aldehyde or functional group present in the monosaccharides or general carbohydrates. The functional group mainly is carbonyl containing compounds. It's maybe an enolic or in the ketonic forms. So it is polyhydroxy, aldehyde or ketones. So in the general classification, we have seen like it's monosaccharides, which is based on the number of carbon atoms involved in this. Trioses means 3, tetroses 4, pentoses 5, hexoses 6, heptoses 7, it goes on. And in case of oligosaccharides, it is, if it is 2, it is disaccharides, and if it is 3, it is trisaccharides, and 3 to 10 are called as oligosaccharides. And more than that comes under the category of polysaccharides. This has been told earlier, that is starch and cellulose. So this is some of the examples where the functional group is the carbonyl compound, where it is it is connected by a covalent bridge with a hydrogen. That is, it is having an aldehydic functional group. So it comes under the category of aldose sugars. So aldoses are classified according to the number of carbon atoms. If it is a triose, it is the first compound is glyceraldehyde. The second one is tetrose and ribose, fructose, etc. So we are having the further continuation of this. So you may get a question like this, like aldose triose. That means this is the glyceraldehyde. This is simple molecule which we can see glycerin. From glycerin, if you remove glyceraldehyde is derived from the dietary alcohol glycerol. So this is a derivative of glycerin. So your next one is aldotetroses. There are two forms, erythrosperm and threosperm. So they differ in this configuration. We are going to discuss the same in this other slides. Erythros and threos, these are having 4 carbon atoms, and they differ in one particular carbon. And this configuration, that means arrangement of the atoms in the space, differs in one particular carbon atom. So they differ in one particular carbon atom in their structure. Rest other fragments are the same. So in the second carbon, we can see that there is an interchange between the functional group hydroxyl group. So there are this the sorry, this is the starting material for other glucose, other sugars or monosaccharides like pentoses and hexoses. So these comes under erythrose family and this comes under the triose family. So this will be like you are adding one carbon atom extra. So from triose, we are adding one. This is Fischer-Kilani synthesis, where we are going to study in detail. So aldotriose, aldotetrose, aldopentose, and aldohexose. So these are the isomeric forms of the hexoses. So we are concentrating on glucose, which is mainly present in our food materials as well as which is the important source in the biology. So gluconeogenesis, glycolysis, all these breakdowns we are studying. So we are concentrating where we are seeing about 1, 2, 3, 4 chiral atoms. So based on the number of chiral atoms, we can find out how many optical isomers are possible. So this is from erythrose. If one carbon is extra, it is ribose and ravinose. And to triose, if you add extra one carbon, it is xylose and lysose. And these are the other forms where we can see these are called as epimers, where there is a small change in one particular carbon atom. So we can say like glucose nanodes, these vary in one particular carbon, that is, they are the epimers. I hope going on, my voice is okay. Is it audible, sir?
Ma'am, it is audible only, no issues, but slightly slight sounds is coming from your background. Otherwise, it is okay, ma'am. You can continue with it, ma'am.
Okay, I hope I am audible. So this is a chiral carbon. Based on the number of chiral carbon, you can tell the number of isomers, optical isomers available. If it is 1, then you can say 2 or 1. This is the formula to calculate the number of optical isomers possible with the number of chiral atoms. So chiral carbon is nothing but a carbon atom which has this breaking. Thank you.
Madam, you are on mute, madam. நீங்க பேசுறது கேட்கல.
Ma'am, please do unmute and then continue with lecture, ma'am.
Madam, voice கேட்கல.
There is a chiral carbon. There is a chiral carbon present in most of the monosaccharides. Now, am I audible?
Yes, ma'am.
Break agudunga.
Slight break agadu, madam.
Okay.
It's otherwise it's okay, ma'am. Continue, ma'am.
Okay. So there is one chiral carbon present in all the most of the trioses, tetroses, and pentoses and hexoses, whatever we have seen so far. And the chiral carbon, based on the number of chiral carbon atoms, we will get the number of optical isomers. That's what we have discussed in the previous slide. So the formula used is 2^1, which represents the chiral carbon. The chiral carbon is nothing but an asymmetric carbon atom, which is an asymmetric carbon atom, which is having carbon atom surrounded by 4 different groups of atoms or 4 different atoms which differ in their chemical environment. So these are some of the other examples. So except by dihydroxyacetone, all other compounds comes under the category of optical active isomers. Coming to the next slide. So this is the pictorial representation of glyceraldehyde, which represents the configuration, of D and L. When the hydroxyl group is on the left side, it is L-form, and if the hydroxyl group is on the right side, it represents the D-form. So this represents only the spatial arrangement, that is how the atoms are connected in the space. So D and L, if we are writing D glucose, it indicates that the hydroxyl group is on the right side of the molecule. So we are taking this simple molecule as the standard. This glyceraldehyde we are taking as a standard, and we are calling other glucose based on this connectivity with this standard. And this type of configuration is called as relative configuration. So the configuration is related with a standard like glyceraldehyde. So this is called as relative configuration. So the sugars which are derived out of D-glyceraldehyde, capital D-glyceraldehyde, this is called as D series, and those with L are called as L series. So D and L represents the spatial arrangement where the functional group, the hydroxyl group, is on the right means capital D, and if it is on the left, it is capital L. There are examples of tetros, erythros, and this is an example for hexose, aldohexose. So aldehyde is present, and we are having 1, 2, 3, 4, 5, 6. So 6 carbon atom, and this is the hexose, aldohexose. So the functional group is aldehyde, so aldohexose, that is glucose. So we are taking the carbon atom connected with the primary alcoholic group, and we are comparing with that of this. So it is like top, which is given in the stereochemistry. We are having, if the hydroxyl is on the right, it is D glucose. If the hydroxyl is on the left, it is L glucose. So epimers. So epimers differ only in one particular. So we are having, this is the structure of glucose, where we can see the hydroxyl group is arranged in reversed in the third carbon atom, and you can see that there is a change only in one particular atom, carbon atom. So they differ all other arrangements, the first, the second, the third, all these arrangements remains the same. So rest of the molecule are same, and they differ in one particular carbon atom. This is called as epimers. Anomers. Coming to the anomers, these are formed by, these are a glucopyranose structure where you are having a ring way of exhibiting. There are two ways. One is the Fischer projection. What we have seen in the earlier slide is the open Fischer projection formula. And anomers, they differ in one particular atom. So the glucose can react with aldehyde, that is the inter-reaction between the functional group aldehyde and alcoholic group. So this is a characteristic functional group reaction of the carbonyl group, where the carbonyl group reacts with alcoholic group to give you an additional compound. This additional compound, based on the uh, number of carbon atoms added, it may be called as chemiacetal and acetal. So in case of glucose, when the aldehyde group of the first carbon atom reacts with the fifth carbon atoms, it forms a chain, or it forms a ring. This ring is called as the chemiacetal conversion. So the glucose is represented as hemiacetal by a pyranose structure. Pyranose means we are having a heterocyclic ring with oxygen, six-membered heterocyclic ring with an oxygen. So the isomers which differ in the connectivity in the fifth position by when the hydroxyl group is on the upside or downside, above the plane or below the plane. Based on that, we can call it as alpha form and beta form. So this is what explained here. So we have to remember that the anomers are also once again epimers, where the anomeric carbon is the interconnectivity where it results between the functional group aldehyde and the alcohol present in the monosaccharide itself. So this is what I have told. Pyranose ring. It's a ring which has a heteroatom. So this is a six-membered ring. This is a cyclohexane ring where you have an oxygen ring, sorry, oxygen atom. This is called as pyranose. So this is how it has been formed. So the aldehyde group gets reacted with the fifth carbon and there will be a formation. So the oxygen atom is shared and the hydroxyl group is transferred here. So hemiacetal formation is based on the number of reactive groups. So it is an example for addition reaction of carbonyl group. So it comes under in the first year we would have studied about the functional group reactions of carbonyl group. So acetal, hemiacetal, all these will come under the carbonyl group addition. So addition reaction, this is an example. So most of our structures, they most of the glucose, it will be exhibiting in alpha D glucose form or beta D glucose form. That is, they are connected internally to form a cyclic structure that is called as interconversion of glucose. The open chain ring, so far last in the last slide we have seen in the Fisher projection has been converted into a ring that is called as Cabot projection. So this is how it has been formed, and this is what I have told you how this is the oxygen is shared and the hydrogen is transferred to the aldehyde group. So the hydrogen goes here and the oxygen is bridged. So this is how alpha and beta differs in the way they are connected by one particular, they are arranged in one particular carbon atom. So anomers are one which differs only in one particular carbon atom, and that is they are the connectivity. So the first portion, see, you can see that the hydroxyl group is down, means that is it is below the plane, it is alpha. If it is above the plane, then it is beta. So it is denoted here. If it is below the plane, it is alpha, and if it is above the plane, it is beta. So coming to the next sugars, that is keto sugars, there are some examples like fructose, which are represented as fructopyranose forms, where alpha and beta similar to aldose. Here they differ in the ketonic arrangements. So these are other way which gives, there are other heterocyclic rings like pyranose and pyranose. So pyranose is a six-membered ring and furanose is a five-membered ring. So in case of smaller rings, we can represent, and ketonics mostly the ketonic sugars are represented using the five-membered ring systems. And we can say always that the primary alcoholic group present in the ring structure is above the plane. So it is given by the solid bond. So this is the strong, this is a thick bond which indicates that this is a beta linkage. So this is a beta linkage which indicates this one. And fructose, it is represented by a furanose structure where we can see this alpha and beta fructose. Fructose closes on itself to form a furanose structure. So these are the other representations. Coming to the next category. So far we have seen about the chemistry of monosaccharides and its structure and various representations using open chain form and the cyclic form. Now we are going to see about the disaccharides. The disaccharides are combination of two monosaccharides. If they are same units, they are called as homosaccharides, and if they are different, it is called as hetero. So there may be two units combined. So two alpha D glucose are united, are connected through oxygen bridge to give you maltose. And here the galactose ring, it is going for the connectivity with alpha D glucose to give you lactose. So these are some of the examples of disaccharides. So coming to oligosaccharides, oligosaccharides means simple example is raffinose, which is present in the peas and beans, and they are connect. The units of raffinose is beta D galactose, alpha D glucose, and beta D fructose. So these three units are connected. So it is oligosaccharides where 3 to 10 units are monosaccharide units are connected. And coming to the polysaccharides, so this starch, the starch, available starch is in two forms. One is the amylose form and amylopectin forms. So we can see the linkages, there will be a difference in alpha 1. The glycosidic linkage variation will be there in amylose and amylopectins. So amylose compared to amylopectins, amylose will be unbranched. Amylopectins will be more branched, and amylopectins are similar to animal polysaccharides too. So this is one example for your GPAT preparation. Amylose, on its reaction with iodine, it will give you a deep blue purple color. So iodine will be giving you a deep blue purple color with iodine. So amylose on reaction with iodine will give you a deep blue purple color, which is a characteristic chemical test to know its presence. So whether it is amylose or amylopectin, iodine test will be a test for identification. Amylopectins, these are made up of long chains of glucose, and they are connected at 1,6 branches every 24 to 30 units. So every after this, it will be connected. So that means there will be two ways they are connected. That is 1,4 alpha glycosidic linkage is connected with 1,6. So this way they are branched. Amylopectins are more branched, and this is seen commonly with other glycogen type animal starch also, where we can see the highly branched chains, which is similar to amylopectin present in the plant starch, which is a polysaccharide. And coming to the last one, it is a cellulose, which is present in the cell wall content of the plant materials, where we can see that the connectivity is even more strong. So that when we are taking solid fiber, with the solid waste are removed when we are taking the fiber content in our as an adjuvant in our food therapy. So when we are taking fiber enriched materials, they are also having more number of these type of branches where the glycosidic linkages are more strong and they are more branched. In case of your previous amylopectins, it is 24 to 30. Here it is 300 to 3000. So we can expect a question like what is the branch? It is beta 1,4 glycosidic linkage, and how many number of units are connected? A macro 300 to 3000 glucose units. And this is what cellulose we have discussed already. It is most coming to the very important question, muta-rotation. Alpha glucose and beta D glucose, when they are dissolved in water, they form one, the optical rotation or the specific rotation. When they are kept in a polar, when they are dissolved, they will come to an equilibrium. That is, they will meet at 52.5. So when you dissolve the glucose in water and you keep it in a polarimeter, you can see that the specific rotation will be equal to angular rotation into cell thickness of the cell, which is equal to plus 52. Plus 52 means it rotates plane pole. Plus indicates the optical activity. Plus means it rotates the plane polarized light towards the right. So when you see a DNS solution, it means dextrorotatory glucose solution. So it rotates. It also indirectly gives you the configuration and its usage. So biologically, D-glucose form is active, or it is an energizer, so which will mixed with a normal saline in case it is used as an energizer or to treat any like diarrheal disorders, water during dehydration states. So muta rotation is when you are having the alpha pyranose, which is having a different alpha pyranoglucose will be having a value of 111, and it will come to 52 degree, and beta will be having plus 19 and it will be rise to plus 52. So there will be a equilibrium and the value is 52. So the time in the meantime, these two will be meeting to get open up to form the D-glucose form. So that means the pino structure, the ring structures are open and they are forming a open chain D-glucose. That is called the hemiacetal is converted into the open D-glucose. So the change in the specific rotation is noted, and this is what muta rotation means. So here there is a ring, and here this again comes to the normal, where you can see that the bridge is not normal. So the D-glucose, it will be having 52.5. So there are some of the reactions of glucose. According to your syllabus, you will have some like oxidation reaction because it's an aldehyde. Aldehyde on oxidation will give you an acid. And so they will be, there are some oxidation reactions which we will be doing in your regular laboratories. So glucose on oxidation will give you gluconic acid and glucoric acid by means of bromine water and nitric acid. And also with Tollens reagent, you will get a silver mirror. And with Felling's reagent, what we are seeing in our lab, if you treat with copper sulfate solution, you will get red precipitate. So with Felling solution, you can come to know that whether the monosaccharide present is a reducing sugar. So when your monosaccharide, when it gets broken, when the disaccharide is broken and it is made up of a reducing sugar, you can easily identify by Felling's test. So these are other reactions where glucose is reduced to sorbitol, and it reacts with hydrogen cyanide. So this is again the functional group reaction where cyanohydrin in addition and with the hydroxylamine. So this is nitrogen containing compounds are added. Nitrogen containing compounds are added to the carbonyl group in order to get the addition compounds. This is carbonyl addition reaction where you get cyanohydrins and oximes. Similarly, the glucose reacts with the penta-acetic anhydride to give the penta-acetate where the replacement of hydrogen takes place. And it also reacts with methanol to give you the glycoside, methyl glycoside. So these are some of the reactions of the OH group. Coming to the other reactions, glucose on reaction with calcium hydroxide gives calcium glucosate, and it on reaction with concentrated acids, it will give open chain compounds like levulinic acid. And there are some other reactions like phenyl hydrazine reactions and ozone formation, which is the characteristic reactions of glucose. So glucose on reaction with the phenyl hydrazine, step by step, it will give the hydrazone and ozone formation, which is the characteristic test. And this is Fischer-Killarney reaction where you are adding the chain lengthening reaction from aldopentoses. This is the aldehyde group, and this is the aldehyde group where the aldehyde is the chain is extended. So we are adding 1 to hydrogen cyanide addition. I'm getting some messages like I'm not audible now. Is it okay?
Ma'am, it's okay, ma'am. I think it is proper.
Okay. Okay, sir. Okay. So the
If
hydrogen
anyone,
cyanide is added, and yeah, I got a message, a direct message.
okay, ma'am. Just go ahead, madam. I think no complaints from other
Okay.
participants. So just carry on now.
Okay, thanks. Okay, sir. The cyano addition takes place, and the cyanide will go for hydrolysis. Hydrolysis will give you the carboxylic acid. So again, this carboxylic acid will be during heating, it loses a molecule of water to give you a compound, and during reduction. So this is chain lengthening reaction of glucose. So chain lengthening reaction where the pentose, that is 5-membered sugar, gets converted into aldohexose by the series of reaction where hydrogen cyanide is added followed by the hydrolysis, and during heating it forms a cyclic, and then reduction gives the open chain compound aldohexose. So now we have added one more CHOH group. So the addition of or extension of the glucose takes place by this way. So when you have a glucose, it may get converted. When you have a fructose, it may go for an interconversion. That is, it may go for a keto-enoterism, and this again it will get fructose will be converted into the glucose, and it will give you the aldo reduction reactions like Benedict's text and silver mirror test. So the ketones on long heating, they may get converted into enol form, that is keto-enol. Tautomerism will take place, and then they will answer the characteristic reaction with the chemical reagents like Tollens reagent. So there are some reactions. The rearrangement of the monosaccharide to give a mixture of isomeric sugars is called as Van Eegsten rearrangement. So this I have taken for some of the reference, which may be a problem solving question. Then this is what I have explained you. The cyanide ring, a cyanide bridge is converted into the acid group and conversion to a lactone, and then followed by the various reactions to give you the additional CHOH. So this is called a Fischer-Kilani reaction, where the arabinose gets converted into two epimers, D-glucose and D-mannose. There are certain chain shortening reactions. These are called as degradation reaction, where we are going to shorten by one carbon atoms. So the hexose may be converted into pentose. The pentose may be converted into tetrose. These are called as degradation reactions or chain shortening reactions of carbohydrates. There are two categories. One is rough degradation reactions. Other one is called as Wolff's degradation reactions. So they act by two different mechanisms, where this is explained in these slides. So this, from glucose, you are getting a pentose. So glucose is getting converted into arabinose through a series of reactions. So in the chain lengthening, you got one from pentose to hexose is called as chain lengthening. So the method used is Ruff's degradation method, where we are using bromine water, calcium carbonate, and hydrogen peroxide to get one carbon reduced by means of carbon dioxide evolution. So this is how Ruff's degradation takes place. And then next is Wolff's, where we are going by hydroxylamine reaction, and we are from aldohexose we are getting an aldopentose. So these are some of the model questions. So gum hati, it is classified. So when you take a resin or gum blacky substances, it is a carbohydrate. So mostly when you want to test gummy substance resin, it will be a carbohydrate. So any gums will come under the category of carbohydrates. Then stereochemistry of cyclic carbohydrate is known as anomers. So the stereoisomers, which are representing the alpha and beta form of glucopyranose, which varies at the one carbon atom, is called as anomer. And if if there are two monosaccharides, if they differ in one single carbon, they are called as epimers. So example is glucose galactose, glucose mannose. So they vary in one particular carbon atom. Rest of the chain will be the same. So these are some of the questions. Which of the following is the example of invert sugar? This we know, sucrose. And diastereoisomers, where which among the following correctly defines diastereoisomers? Diastereoisomers are the isomers which contains more than one number of chiral at carbon atom, and they differ in their way. They are not optically active. Sorry, they are optically active, but they are not mirror images of each other. They differ in the way of rotating the plane polarized light. So they define both physical and chemical properties, that is diastereoisomers. And the galactose and glucose are coming under the category of epimers. So these are some of the questions. Before I conclude my speech, I want to thank all these members of Pharmacy Alumni Association, Medical College, has given me a great support during all these days. And Indian Pharmaceutical Graduate Association and their team for their valuable time and support. And I also thank my management, the principal, and the team of Sri Abhirami College of Pharmacy, Coimbatore, for their constant encouragement and support for all my professional activities. And before concluding my talk on carbohydrates, I want to tell you something which is useful in the research. Earlier days, I'll take 5 minutes to complete it. Earlier days, we have chemical degradation methods, what we have seen, Ruff's degradation, Wolff's degradation, and chain lengthening process like Fischer-Keller-Kellini process. But nowadays, when you are as a phytoconjugated researcher, I want to highlight only two things now, and I will hand over the session to the organizing committee. When you have a secondary metabolite, primary metabolite, even these primary metabolites, you find something interesting in that research. You can, and if you are getting a small crystal out of your chemical analysis, or in your beaker, you're seeing a small crystal, that crystal, you can go for a structural elucidation. Nowadays, we are finding so many interesting small molecules which are still in the pipeline, many therapies like anti-cancer therapies. So we are having more sophisticated spectroscopic techniques, which are hyphenated techniques associated. So we can find out if you get a crystalline form of any type, and if it is new, we may be losing a novel compound. So the crystal may be evaluated by, our crystal may be studied by X-ray diffraction studies. So when you get a crystal, small crystal, which is 5 millimeter in size by all length and breadth, you can subject it to X-ray, and you will get a beautiful 3-dimensional, which is not possible in the earlier days. What I mean to say here is, we need to be little associated with the hyphenated techniques and updated technologies and interpretation while we are going for a phytochemical research. With this, I thank once again all the organizing team and the students. I wish you all the best. Believe in yourself and put your hard work and perseverance. Definitely your hard work, continuous learning will make you shine bright. Thank you one and all. Thank you for your patient listening. Thank you.
Thank you so much, madam. Congratulations. And you put very precisely and very crisply, nicely explained that carbohydrates. I think all the participants will get benefit out of it.
Thank you, sir. Thank you, sir. Thank you for the beautiful introduction or also conclusion. Thank you, sir.
Thank
you. Sir, is my slides visible?
Yes, madam. It is very much visible, ma'am.
Okay, sir. Thank you.
Meenakshi ma'am, Dr. Jaikumari madam.
Sir, good morning, sir. Good morning.
Very good morning, madam.
Join. Ipada madam, Lakshmi madam presentation.
Welcome, ma'am.
It is starting, ma'am.
Yes, sir. Yes, sir.
Okay.
Please
Since
tell
no
me.
questions, ma'am, since no questions for the first session, we will move on to the second session. Now I request Dr. Jaikumari madam, Professor, Head of the Department, Wales College of Pharmacy, Chennai, to give a speaker introduction for the second session. Ma'am, over to you, ma'am.
Yes, sir. Thank you, sir. Very good morning to one and all students and also all the team members and Lakshmi madam also. Today, I'm very happy to introduce my long friend as well as a well-known personality in pharma field, especially in pharmaceutical analysis, Dr. K. Lakshmi. Presently, Dr. K. Lakshmi working as a Professor Dean, Chettinad School of Pharmaceutical Sciences, Chettinad Academy of Research and Education, Kelambakam, Chennai. She graduated from SRM College of Pharmacy in 1997, and he post-graduated from Pharmaceutical Chemistry from Madras Medical College, Chennai in the year 2000, and he completed her Ph.D. in SRM University in the year 2011. Apart from that academic qualifications, he is a well-known personality. He has completed many online courses, completed PG, DI, PR, IGNOU, New Delhi, and many certificate courses. He has a recipient of the many online certificate courses from NPTEL and SOIA, and MOOC course on the Start Your Venture from IIM Bangalore. She also recipient of the online certificate courses on the data science and the XLRI GEMSET 4. So she is, apart from his pharmaceutical analysis, he is a well-known personality in biostatics, calculations, Excel and everything. And then coming to the awards, he has received many awards. A few I have to quoted here. He received a travel grant award from AICT and DST, and visited a number of countries, Turkey and Amitabh, for international conferences. She also recipient of the research project from DST and UGC, which is worth about 28 lakhs and 42 lakhs and 80,000. She is a recipient of many project proposal from DST and AICT and UGC also. He published many articles in Scopus and will impact good journal, nearly more than 65 in national and international journal, a total of 520 citation. She attended many conferences also. He presented many papers in conferences, more than about 50 as a main author and as a co-author. She guided 50 number of UG projects and also a PG level also. Currently, he is guiding PhD scholars about 3 numbers. Coming to his research expert, he is a well-known research expertise in the analytical method development and validation using UV visible spectrophoton, HPLC, HPTLC, and commercial tools, PLC, toolbox, and other or software technologies. He is a well-known personality in using many software technology in pharmaceutical analysis for method development and validation. He organized many webinars, workshops, seminars, and conferences at state level, national level, even at international level. Delivered many invited lectures and talks in many webinar, workshops, seminars, and faculty development program. Editorial board member and reviewer in many national and international journals. Life member of many professional bodies like IPGA, IPA, APTI, CSI, and IASCP, ICWs, like that. It's going on endless. She also a doctoral committee member, Wells Institute of Technology, Vistas, and SRM College of Pharmacy, Chennai also. She is one of the DC member for my students. She is a well-wisher of all the PhD students. She received many best paper awards also. She has a total experience of 20 years in the teaching as well as in the research experience. With a few introduction, he also have a different responsibilities in different current institution. He have some responsible person in number of board members. For example, I quoted some here. Is a chairperson for Board of Studies, a PhD supervisor for 2 candidates, member secretary for Institutional Review Board, IRB, and he is a SPOK, that is a SWAM in NPTEL local chapter also. He is also a member of the Institutional Innovation Council and Students Counseling Center. So like that, madam's profile is going on lengthier. Due to lack of time, I given only a short profile only. With this few note, I welcome Dr. Lakshmi K. Lakshmi for your presentation, valuable presentation in the spectroscopy, madam. Thank you, madam. Welcome, Lakshmi.
Thank you, ma'am. Thank you very much for the nice introduction. I thank J. Kumari madam personally as well as officially, and I thank all the organizers of Pharmacy Alumni Association as well as IPGA Tamil Nadu branch for providing an excellent platform for GPAT coaching. And I am very happy that I can play a small role in this extensive opportunity provided for the students. More than all this credential, I prefer to be a good teacher. Students, please forget about all the other things. I want to be a good teacher, and whatever I teach, I want to convey that to the students. And I thank all the students who has been in my profession, in my career, who has brought me to this level, because if students were not there, I would not have studied. I am a good learner, first of all. I have become a good learner because of my students. I have learned all this during my 21 years of this career. Whether I have studied properly in my B.Pharm or not, but I have learned many things during my 21 years of this teaching career. So for that, I should first thank my students for providing me all this excellent opportunity. Okay, so now today the topic what we are going to discuss is on IR spectroscopy. First of all, I welcome each of the student from various pharmacy institutions. Maybe every Sunday you may be attending regularly, or you may be new for this Sunday, whatever it may be. So 2 hours you are spending for your GPAT coaching, and we all know that pharmacy is an interdisciplinary profession. So last 1 hour you were discussing you all that which would have been in your mind is about carbohydrates. Now suddenly I am switching over to IR spectroscopy, which is a analytical tool. So, but of course, you cannot master in each and every topic at this level, but at least an overview of each and every topic is required for you to move forward in your career, right? So IR spectroscopy, you study this topic. I don't know whether fourth year students are attending or third year students are attending. So this is a topic which you will read in a modern pharmaceutical analysis, modern instrumentation techniques or pharmaceutical analysis, where you read different instrumentation techniques, right? So when I have gone through your syllabus, so only FTIR spectroscopy is given, not NMR and mass. So I thought I'll restrict my talk on FTIR spectroscopy. So spectroscopy technique is a wonderful thing. What we use it for analyzing each and every compound. See, if analysis is not there, there is no research at all. You may be a good chemist, you may be good in pharmaceutics, you may be good in pharmacology, you may be good in pharmacognosy. But for everything, in order to prove your research or in order to prove anything, you need analytical tools. So I always tell my students analysis is like a shadow, but somehow many of the students have some aversion towards analysis subject, but it's very easy. Most of the things are just an imaginary one, and the concepts doesn't change whether you study in UG level or whether you study in PG level or even at the higher level. The basic principle will never change. Whatever you studied in UG, you are going to same thing you are going to study in PG. Only the applications vary from one level to the next level. So the understanding of the concept is very, very important here. So I'll take you today through the IR spectroscopy. Hope you will understand. So this starts with, like, we start from the basic understanding, like electromagnetic spectrum. We have lot of rays that are there. You all know about light. Light travels in the form of waves. So it has a crest and trough. And the distance between two crest or two trough is called as a wavelength. So depending on the wavelength, we classify the different light radiation into different categories. So we have X-ray, we have all this UV, IR, microwave, radio waves, all this are called as electromagnetic spectrum. Why they are called as electromagnetic spectrum? Because they possess electrical property and magnetic property. Simple. They travel in the form of waves. Since they are possessing both electrical properties and magnetic properties, they are called as electromagnetic spectrum. This is enough if you know this level, right? So depending on the wavelength in which they travel, they are classified as UV, visible, IR, NMR, all this, right? So we are now going to discuss much about IR radiation and why all these radiations are coming into picture. See, we play with the compounds, right? So even in earlier session, there was a discussion on carbohydrates. So carbohydrate is a chemical compound. So we have organic compounds, we have inorganic compounds. Either it is from a natural source or a semi-synthetic one or a synthetic one. Everything comprises of compounds, chemistry. So in chemistry, we play with atoms, we play with compounds. We talk in terms of carbon, hydrogen, oxygen, nitrogen, right? So they exhibit certain properties. We simply draw something in a paper, but they are actually existing in our real life. The sari what I wear, the laptop what I possess, the book what I read, everything is made up of some chemistry, some natural source of chemical compounds. So this has certain properties. So they undergo certain changes when they meet this light radiations. So when X-ray is there, it undergoes bond breaking. When UV visible is passed through this organic compound, they undergo a process called electronic transition. That is, the transition is happening in the electronic level. So if it is a compound, we talk as compound as a whole. Then we talk as a molecule, just one particular group, right? Then we talk in terms of atom. Then we talk in terms of electrons. So that is how we go down, right? So even a human body, we take it as an organ system, then the organs, then the tissue level, and then the cellular level. Likewise. So UV visible radiation, when it is passed through a compound, it undergoes electronic transitions. Whereas today our concern is on infrared spectroscopy, where infrared radiation is used for analytical purpose. So what kind of thing you are concentrating when you pass the infrared radiation? We are concentrating on the vibrational aspects of a compound. So if I take a compound will undergo all three aspects: electronic aspects, vibrational aspects, and rotational aspects. So now using IR, I am concentrating on the vibrational aspects of particular compound. And remember, every compound will have all these three. They will have a combination of electronic transitions, vibrational transitions, as well as rotational transitions. But we are concentrating one at a time in order to do the analytical procedures. Analysis means qualitative and quantitative analysis of compounds. So here in this slide, I have shown here in electromagnetic spectrum, what are the ranges that covers the infrared. So in infrared, again, we have subdivisions like near IR, mid IR, far IR. So you can see here the wavelength. In case of UV, you would have studied in terms of nanometer. Whereas in case of IR, it is expressed as centimeter inverse. It's like 1 by wavelength in nanometer. We will be seeing that in the subsequent slides, right? So as of now, you remember IR radiation, it actually taps the vibrational frequency of the compound, and it is divided into three portions: near IR, mid IR, and far IR. But what we use predominantly is the mid IR region. Near IR, separate spectroscopy. Near IR spectroscopy is separate, and that applications are totally different. But what we are going to talk today is on mid IR. So this is the commonly used, and the range is from 500 to 4,000 centimeter inverse. And far IR is 5 to 500. Nothing wrong in knowing what is beyond and what is on the left side. So mid is 500 to 4,000 centimeter inverse. Beyond that, it is 4,000 to 14,000, whereas far IR is 5 to 500 centimeter inverse. So this is what you need to know from this particular slide. So each and every slide you learn 1 or 2 points that is absolutely sufficient for your GPAT is concerned. This may not be sufficient for your final examination. Right. So this is the simplified infrared spectrophotometer. Actually, we are not concerned again about the hardwares that are used in this. We are more concerned about the application part of infrared spectroscopy. But still, we should know what are the source and what are the other components that are being used in a spectrophotometer. So you might have already studied in UV also. It contains source which provides the necessary radiation. So in UV, the source will produce UV radiation, whereas in IR, the source will produce infrared radiation. So that radiation has to reach the sample. That is what is happening here. The radiation reaches the sample. The sample is placed between sodium chloride plates. Why the sample is placed between sodium chloride plates? Sample can be placed between sodium chloride or potassium bromide. These two are commonly used because only sodium chloride and potassium bromide will not absorb IR radiation. whereas glass, plastic, all other materials will absorb this particular IR radiation. And polystyrens will also not absorb. So generally calibration is done by using polystyrene films or polystyrene strips. Okay. So here the sample is placed between the two sodium chloride or potassium bromide plates, and after which the radiation is sent to the detector in order to record the IR spectrum. So ultimately we will have sample in hand and finally the IR spectrum. So we need more understanding within this sample and IR spectrum. That is what we will have in hand. Other things you cannot see at all, but still we are very much concerned what my system has. So if you are buying a mobile, though you are not concerned, you cannot open and you cannot see whether what processor is there. But still you are interested to know what processor it uses for functioning of my mobile or my laptop. Likewise, so we need to know what is the source that is used, what is the detector that is used, what are the monochromators that is used. Just the name of the components are enough, that we are going to deal in detail. So here we call this IR spectroscopy as a Fourier transform infrared spectroscopy. Earlier it was not so. Earlier they were using only infrared spectroscopy, but later on there was a very much requirement for upgrading the instrument to Fourier transform infrared spectroscopy. So why this Fourier transform? It uses Michelson interferometer, and then this particular instrument also uses a methodology, a mathematical calculation called, that is formed by Fourier. So in order to convert the time domain curve to frequency domain curve. So when they initially developed the IR spectroscopy like that of UV spectroscopy, finally they were surprised to get a structure, to get a spectrum like this. So this spectrum was like a time domain curve. It's called a time domain curve. Number of hits that is provided to that particular instrument with the intensity. So people could not able to, researchers could not able to find out what it is. They could not do any interpretation. So what they have done is with the help of Michelson interferometer and with the help of Fourier transfer. These two are the new thing that is added to the current FTIR what we are using. So this Fourier transformation is a mathematical calculation that converts this time domain curve. If you know this term, that is enough. Time domain curve into frequency domain curve. This is what we are currently using it. Frequency domain curve is in x-axis wave number and in y-axis it is intensity. So this is a very interesting thing, and that's the reason nowadays there is no simple IR at all in market. We have only FTIR, which uses interferometer and Fourier transform. Is a mathematical calculation that converts time domain curve into frequency domain curve. That's it, right? So this is the flow diagram or optical system diagram for IR spectroscopy. This again, it is very important so that you should know what are the components and how they are placed inside an instrument. So why many times students are finding it difficult is we cannot open this and show how it works. These are all just an imaginary thing. So you need to imagine, okay, there is a light source. So from the light, the beam actually splits. This is a beam splitter, and it splits into two and it reaches here. Again, another beam splitter, and you can see two mirrors are placed. One will be movable mirror and another one is the fixed mirror. And then it reaches another mirror, concave mirror, and then it enters into the sample chamber and finally to the detector. So there will be diversification of light, there will be converging of light, many process takes place. So where to keep this? What is the focal length? What is the split width? See here, it is traveling to a small slit. So what should be the slit width? All this, the engineering, biomedical engineering people will take care. So we are not concerned about this. We want to know just what is there actually inside the instrument. So this is the entire setup here is called as the interferometer. So these terminologies are very important. You should know that yes, my system contains interferometer. What is interferometer? It has a beam splitter and one fixed mirror and one movable mirror. So that is required in order to convert the time domain curve into the frequency domain curve. And this gas laser actually calibrates, it's automatic calibration of helium and neon gas. So it's automatic calibration. So that is what is happening. And there will be a sample chamber. Sample is kept in between the sodium chloride or potassium bromide. It is sandwiched between sodium chloride or potassium bromide. And or sometimes it is prepared in the form of a very thin pellet and it is placed on the path of the IR radiation. And finally, the spectrum you will get from the detector. So this is again another diagrammatic representation because every time I want to show that representation, whichever is nice, because you may understand and you may use which diagram suits you. Okay, so this is again the interferometer. You can see here it results in the formation of interferogram. From interferometer, you will get only the interferogram. Interferogram is converted into IR spectrum by means of this Fourier transformation. So interferogram is nothing but the time domain curve. This is the frequency domain curve, right? So the spectral range is continuously calibrated with helium and neon laser. This is what is actually happening there. Okay, so we can see little detail of each and every component, what is being used. So more than the engineering part, the application part will be very, very interesting. But as such, you may get some of the questions like what is the light source that is used in IR? What is the light source that is used in UV? So you must be in a position to differentiate. Yes, this is my IR source. This is my UV source. So for that reason, at least we should learn what is what, right? So light source is the one which is producing the IR radiation. See, whatever light we use in our household is a tungsten lamp, right? So that produces visible radiation, whereas this is for IR radiation. And it cannot use glass again because IR is absorbed by glass. So it is made up of other materials. So you can see here, the first type is the nursed glower, and it comprises of rare earth metal oxides, zirconium, thorium, all this. And always remember, there is a connection between heat and IR radiation. So when you go to physiotherapist, sometime if we have inflammation, they have a higher lamp and that is actually focused to your skin. You can feel the heat there. So it's just the reverse. When a metal is heated to some extent, they also produce IR radiation. Very interesting concept actually. Certain things are very interesting and we cannot recreate or we cannot redefine them. So when IR radiation is focused on your skin, right? So it produces heat. Similarly, when some metal oxide, so why we are using zirconium or thorium, why some specific compound? Because they can withstand this particular heat, 1200 to 2200 degrees. What happens? This produces IR radiation of this particular wavelength. The radiation which is produced by them is of specific wavelength. That's why you need different light sources, or else you don't require one lamp for all for UV visible. That is not possible. UV has different concept. IR has different concept. In IR, again, for covering this particular range, you use one source. For covering another range, we use another source, right? So this is what it happens. So there should be a good control over heating, because if you overheat above this may damage the filament or whatever it is which is being used in that particular light source. And second one is the glow bar source, where they use silicon carbide rod, and that also has similar application. Only thing is you need to remember the names and different materials, because each and every source is being named after the material what is being used. But concept is same. There is some material that is getting heated up. So because of that extreme heat, they have a capacity to produce a IR radiation, right? So next one is the incandescent wire source. So it is the nichrome wire, nichrome or rhodium wire that is electrically heated. So you can see there the concept is written as it is same principle as that of the nurse and clover. So this produces the light and IR radiation at a particular frequency. Or sometimes even the carbon dioxide laser can be used. It's not absolutely the pure carbon dioxide which is used. It's a mixture of again 70% helium, 15% carbon dioxide, and 15% nitrogen. So when this particular mixture is used and they get heated up, they produces the radiation which is covering a range of 900 to 1100. So these are the different sources available. Many times they even use laser source for IR radiation. And mercury arc is another one which can provide far IR, whereas tungsten lamp can even provide a near IR radiation. So what is the major light source? Light source is mainly to produce the IR radiation from what? What I require? I need mid IR region. Mid IR region is from 500 to 4000 centimeter inverse. So I need radiation for this entire range. So for this, I can use any of these sources. What is the major application of this sources? This sources uses different materials, and when this material is getting heated up, they have a tendency to produce IR radiation. Simple. So nurse to globar source, incandescent wire source, CO2 laser. So you make a just small tabular column. Nurse to globar, yes, it is having a material. It is comprising of material. It can be made up of a material called rare earth metal oxides. ZR, CE, TH, yes, it should be heated up so that it produces the IR radiation. Globar source, silicon carbide, then incandescent lamp, nichrome wire or rhodium wire, all this, right? Okay, so what are detectors? Because these are the two major things. We have already seen what is interferometer. Interferometer comprises of different mirrors and a splitter, beam splitter, which can split the light into two, and two mirrors are used. One is fixed and one is movable in order to converge and diverge the waves that are produced or the radiations that are produced. Let us not go into detail of that. Now the detectors, there are two main types of detectors. One is the thermocouple detectors. So here again, now this detector should convert heat into, the IR radiation. When the IR radiation falls on this particular detector, again that produces heat. That's what I said. IR radiation when falling on a body will produce heat. When a material that is heated up, that produces IR radiation. So this concept is used in case of detectors. So when some metals are used here, you can see here metal 1 and metal 2. This H nu represents the source, the IR radiation. So now the IR radiation has passed the sample and then it hits the detector. What happens? There is some heat difference that is created, that is read as a difference in the heat energy, because before you place the sample, there will be constant heat energy that will be produced by metal 1 and metal 2 because of the 100% of IR radiation. When you keep the sample on the path of the IR radiation, it is understood that sample is absorbing some amount of IR radiation. So 100% of IR radiation will not reach the detector. So this difference can be dealt as a spectrum. Okay. So next thing is the bolometer. Bolometer is again, they use the metal like platinum and nickel. That is also giving the changes. That also reads the changes with the temperature. And it is very sensitive when compared to the other detector, what we have studied. And this photoconducting detector is actually the very common thing. This is also used in UV visible also. Here, the interesting concept is your whatever light radiation that travels, H nu is the light radiation, IR light radiation. Okay, in terms of energy, it is given. So quantum of light radiation. So whenever that hits on this particular material, where this material is coated with a semiconductor substance, this has a capacity to emit many electrons. They will absorb all the radiation and they will emit many electrons. And this electrons in turn will hit the another semiconductor, thereby the electrons gets amplified and the current that is flowing in the circuit will also get amplified. And this actually is given in terms of a spectrum. See, this is what is given. What is happening there? Absorption of light by the semiconductor. So there is a decrease in resistance and increase in flow of current. So whenever you have a circuit like this, there will be a flow of current and resistance. All this only will come into picture. And movement of the flow of current is always increased by movement of more number of electrons. That we need to remember. So this number of electrons are amplified in photoconducting detectors. Thereby, there is increase in the current flow. And this increase in the current flow is again, in turn, is very much essential for getting a proper spectrum. The spectrum should be having a good signal when compared to the noise peaks. See, when we take a picture, we talk in terms of pixels. We talk in terms of clarity, right? So when will you get good clarity? When you have a good pixel of that particular picture. Similarly, when the spectrum is recorded, we need a good signal comparing to the noise. Noise is nothing but small unwanted peaks. Signal is something related to our compound, what we are going to study. So that is the reason why we have to use a good light source and good detector. So this photoconducting detector will produce a very good amplified spectrum with a good signal to noise ratio. Signal to noise ratio should be more. Okay, so that is what here another detector is used called pyroelectric detector. So you should at least know the names of the detectors. They are used: thermocouple, then bolometer. They both fall under same category because they are just finding out the difference between the temperature difference before the sample placed on the path of the IR radiation, after the sample placed on the path of the IR radiation. Photoconducting detector and photoelectric detector are something, they are converting that into the electrical charge. The whatever light is that is hitting on that particular material, that is getting converted into the electrical energy, and that is actually measured. So it is having a fast response and very good for the FTIR. That's what is given here. So what are the other components? So we have majorly discussed about the light source and the detectors. Other components are the sample cell. So you can see here, this is a sodium chloride pellet. So sodium chloride or potassium bromide pellets. This is mainly preferred for the solid sample. Very simple, the solid sample and potassium chloride or sodium chloride is just blended with that, and there is a small die set with which we use, we press that and we prepare a KBr or NaCl pellet. And that is actually placed on the path of the IR radiation. And there is a provision for liquid sample holder also. So if your sample is a liquid can be placed on this and then it can be directly kept on the path. So you can see there are different provisions here, but sample will be kept or it will be spread as a thin layer on this liquid sample set. So many times if you refer to books, they would have given it as neat spectrum. Neat spectrum, it doesn't mean that the spectrum is neat in nature. It means that the neat spectrum represents that the liquid sample is directly taken into consideration, not the solid sample. Because you have benzene, you have chloroform, there are certain compounds that gives a and that are liquid in nature, and that can be placed on the liquid sample and it can be recorded. The spectrum can be recorded. Then monochromators, which will convert the polychromatic light into monochromatic light. That is always needed if we want to select one particular range of IR or one specific IR radiation. So that is provided by gratings and prisms, right? So gratings and so prisms are not used because glass should not be used. Whether it is grating or whether it is prism, actually they use, again, the grating is made up of this sodium chloride or potassium bromide. Everything that is even the window through which the light radiation is passing through, even that is made of this alkyl halide. Okay, based on this halides only, sodium chloride or potassium bromide. Glass or plastic cannot be used at all. Even the gratings are made up of sodium chloride or potassium bromide. That is the very important thing which is differing from UV. So you have to remember that point. And this is again the same picture, Michelson interferometer. So you can give a wide picture of that. So laser diode is there. You have a fixed mirror, moving mirror, beam splitter. So everything, IR source, and then the detector sample. You can see here sample is placed almost near the detector. And this IR source is, again, it is provided with helium and neon laser in order to have a good calibration, continuous calibration. Okay, so what is its application? It is mainly used for finding out what the compound it is, for identification purpose, for qualitative analysis. It's not meant for quantitative analysis. If not, IR at least provides information about the different types of bonds that are present. And it is actually easy to use because liquids are analyzed between the salt plates. So even the liquid sample cell is made up of sodium chloride or potassium bromide. Solids can be prepared in the form of a KBR pellet. And there are some small units with FTIR microscope, even that can be utilized. And it is not that expensive. Most of the academic colleges and labs are having FTIR spectrophotometer nowadays. So some theories associated with this, because we cannot skip those theories. A quick review of these theories. So what is wave number? Wave number we are expressing as mu bar. This is the representation of wave number, and it is written as Cm inverse, right? So mu bar is nothing but 1 by wavelength. 1 by wavelength expressed in centimeter, not in nanometer. That's why our unit is centimeter inverse. So frequency can also be calculated. If you know the frequency, you can convert them. And they are interconvertible, frequency and then lambda, wavelength, all this you can find out. And wave numbers, from this equation, we understand that wave numbers are directly proportional to the frequency. Okay. So what are the molecular vibrations that are taking place? I have told in the first slide that it is the vibrational frequency that is taken into consideration. So though we write it as C, single bond C, actually it's not just a bond. It looks like a spring. It is not a single line. The bond is, the real appearance of bond is like a spring. So you can expand the spring, right? You can expand the spring, you can bend them, all kind of things we can do. So similar things are happening in case of molecules also. So they are said to be molecular vibrations. So in that, again, we are considering the two kind of vibrations. One is the stretching vibration and another one is the bending vibration. So even in yoga, we do different postures. We are concentrating on stretching and bending because we want to give some exercise for our muscles. So obviously stretching and bending will be a very important aspect. So stretching is when the bond length, when there is a change in the bond length. How can you give a technical terminology? Stretching is change in the bond length, whereas bending is change in the bond angle. That is what is represented here. Change in the bond length and change in the bond angle. So stretching vibration and bending vibration. And interestingly, stretching vibration will take place in different frequency Bending vibration will take place in different frequencies, right? So in stretching, again, we have subtypes, symmetric and asymmetric. So what we are considering here, we are taking example as 3 atoms, that is the center carbon atom and 2 small hydrogen atoms that are attached. So what really happens here? This 2H is moving away from the central atom. So when both the hydrogen are moving away from the central atom, they are said to be symmetric in nature. When one is moving away and another is moving towards the central atom, it is called as asymmetric in nature. Then in bending, we have in-plane bending and out-of-plane bending. So out of plane is 3-dimensional, towards you, away from you, whereas in plane is just the left side and right side. So in plane bending, what is in plane bending? Here you again have 2 types, scissoring and rocking. So this thing has to be clear because there will be questions related to this also. Scissoring is 2 hydrogen atoms moving towards each other. And rocking is both moving towards right side or both moving towards the left side, right? That is rocking. So you can shake your hands, you can twist your legs likewise. So here out of plane is one is towards you and another one is moving away from you. Whereas wagging is both are towards you or both are away from you. So it's all imaginary. You have to imagine all this. So stretching vibrations and bending vibrations. Why all these are required? Because this vibrations exhibits in different frequencies. And this is needed in order to know what compound you are having. This is very helpful for us in finding out what the compound is, right? Or what the functional group is. For example, this is the IR radiation, IR spectrum. So you can see the spectrum here. The x-axis contains the wave number and y-axis contains the absorbance. Okay, so here this simple compound is taken into consideration, that is carbon dioxide. So in carbon dioxide, if C is placed in the center, both O are on either side, it has a symmetric stretch that will not IR active. If it is a symmetric stretching, so stretching vibration means it can be only asymmetric, right? Whereas bending vibration has different dipole moments, so they are IR active. It means they will produce some signal in the IR radiation. Okay, we will see that little in detail later. So Hooke's law is something associated with this particular IR spectroscopy. You would have studied Beer-Lambert's law in UV spectroscopy. Hooke's law is something related to IR spectroscopy. So that's also very important because the wave number at which it is showing the absorbance is proportional to certain things. That is what is given as Hooke's law. 1 by 2 pi c into root of k by mu. So mu is the reduced mass, that is m1 into m2 by m1 plus m2. So it directly, this wave number directly depends on the frequency and it also depends on the force constant. K is the force constant. That is, if the strength of each and every bond. So if there is a triple bond, that has more strength. So the frequency required is more here. Whereas if the size is more, then the frequency is less. It is inversely proportional. So triple bond will have more strength, double bond will have less strength, whereas single bond C will have less strength still. So when we read the interpretation, that time you will understand this relationship. So M is the atomic mass of each and every atom, because whenever we talk about IR, it is not one single thing. Remember, it is between 2 atoms. So C bond, C double bond, C bond, C triple bond, C bond. We will always talk between the 2 atoms. So the 2 atoms, they are separated by a bond. So the wave number depends on the bond strength. And what is the other aspect? The atom which it has. Instead of the C triple bond C, I may also have C triple bond N. Instead of the C triple bond C, I may also have C triple bond double bond O. Instead of the C single bond C, I can also have O and H, right? So this is what we are trying to understand. Whenever you talk about IR, you will not be talking the whole compound, of course, whole compound, but each and every atom will be taken into consideration. Two atoms will be taken together. It will be studied two atom wise only. OH, C double bond O, C triple bond C, C triple bond N, C double bond C, likewise. So what should be our understanding? The wave number is directly proportional to the bond strength and inversely proportional to the mass of the atom. So if I have more mass, instead of C double bond C, if I have C double bond O, the frequency wave number will be less. So if I have a C double bond C and C triple bond C, C triple bond C will be absorbing at higher wave number. Where it will absorb, that is what we are studying here. So that is said to be the Hooke's law. So you can see here, these are the wave numbers. These are the wave numbers at which they show the absorbance. Very interesting thing it is. So whenever C triple bond C, whenever a compound is containing C triple bond C is placed on the path of IR radiation, there will be a peak at 2150. It means my C triple bond C has absorbed some amount of UV radiation at 2150 centimeter inverse. And C double bond C at 1650. C single bond C at 1200. So now this concept, I am using it. Okay, now whenever I see the spectrum, I have a peak at 1200. It means it is because of C single bond C. I see a peak at 2150. Yes, it means that it is because of C triple bond C. This is how it is useful. So you can see here, this is the example for single bond, double bond, and triple bond. What does that indicate? With increase in bond, there will be increase in wave number because it's directly proportional. Wave number is directly proportional to the force constant or the bond strength. It is inversely proportional to the mass of the atoms. So here, what am I having? CH, carbon is 12, hydrogen is 1. So 3000, whereas here, carbon 12, another carbon 12. See, the wave number decreases. Carbon 12, oxygen 16, the wave number decreases. So with increase in the mass of the atom, the wave number decreases. Okay, right. So what we learn from IR spectrum? The IR spectrum, if I record and give it to you, you have a compound, you will go for a spectrum recording and finally you will get the spectrum. So what do you understand from the spectrum? It will have a lot of peaks and IR spectrum is always given in this term. That is wave number in the x-axis, and from the left end, it will be 4000 centimeter inverse. And the right end will end at 500 centimeter inverse, from higher to lower. And this y-axis will have percentage intensity, not absorbance. So in case of UV, you are measuring the absorbance. So you will write the peak like mountain. Whereas here it will be upright, hanging down, ulta. Absolutely the ulta peaks you will see. If it is absorbance, you will see the erect peak. If it is a percentage intensity, it is the reverse. Why the percentage intensity is taken? I will tell you that. So now this is the spectrum. So what do you observe in the spectrum? So here there are many small peaks are there that you can ignore, and you can see my peak actually starts closer to 100% intensity. So this is how the good spectrum should be. And you can see many peaks here. They have a very sharp thing. And this sharp peak is very much needed. That will give you lot of information about that particular compound, right? So this is another example. You can see very clearly here, it starts from 4,000 to ends with a 600 or 500, whatever it is. And then this is the percentage transmittance. This is how the peaks looks like. You can see many peaks here. So easily you can relate it where the peak is. You can see one peak at 3,100, another peak here, another peak here, and then there is one more peak at this particular range. So you can draw a line and find out where it is. Okay. So, but it is enough if you consider the major peaks, not the small ones can be ignored. Right. So all these are the theories associated with that. We can see here, you will have a strong peak, you will have medium peak, and you will have weak peak. That is because of the different peak intensities will be there. So this OH and NH, depending on the group, the peaks will appear in different places. So if a compound contains OH or NH, then the peaks will appear in this particular region. If a compound contains CH, then the peak will appear in this region. The triple bonds appear in this particular region. Double bonds appear in this region. So from this interesting facts, we can find out what are the groups that are present in that particular compound. And this can be broadly classified into two categories. One is functional group region and another one is fingerprint region. And this is again a very common question which is asked for functional group region and fingerprint region. The region from 4,000 to 1,500 is functional group region, and 1,500 to 700 or 600 is fingerprint region. Here it gives 1,200 to 700. Many books gives different things, but as a general, you can also have it as 1,500 to 4,000. It is functional group. 1,200 to 600. It is fingerprint region. Sorry. So why it is fingerprint region? Because it's very specific, highly specific. Even you can no two compound will have same pattern. Say for example, here they have given an example of acetone and an ester, right? So this is a keto compound, this is the ester compound. So both will have C double bond O in this particular functional group region. Only difference is addition to C double bond O, this will have C single bond O. That can be seen only in the fingerprint region. So that's the reason why it is called as fingerprint, because no two compound will have similar, we don't have same fingerprint, right? Even the right and left thumb are different. So even if twins, they will have different fingerprint. So this is the reason why it is called as fingerprint region, and it has different patterns. It is very unique for each and every compound. So these are the typical wave numbers you can remember. From 4,000 to 2,500, you will get OH, CH and NH. And between 2,500 to 2,000, all this triple bond is seen. And from 2,000 to 1,800, very few bands are seen, particularly for aromatic. From that itself, we can differentiate whether it is aliphatic or aromatic. C double bond O peak will be very prominently seen in this 1,800 to 1,650. And this region, C double bond N, C double bond C, and all these other peaks are there from 1,550 to 650. And this cannot be made thorough overnight. It will come only with a lot of practices. But at UG level, it is enough if you know these things. These things are enough at the UG level. Only PGs and PhDs, when they go for PhD research scholars, they study more, they study in detail all this. But as of now, it is enough if you remember at least this. So OH stretch. What is this called? OH stretch, NH stretch, CH stretch. Mainly the stretching vibrations. The stretching vibrations gives maximum information of a particular compound. So my OH stretch will be at 3600. You have this table. OH stretch at 3600. You close left side. If the peak is at 3600, that is OH stretch. If I see a peak at 3400, that may be a NH stretch. If I see a peak at 3000, that may be CH stretch. That is how you have to interpret the compound. That is how you have to find what compound it is. So here are some of the examples. After example, we can quickly go through some questions which will be useful for your GPAT exam. So actually, each and every compound has certain characteristic peaks. The list is very long, but I am restricting with alkane, alkene, and alkyne. As I told, these things only PG students will read in detail, but just for understanding how the thing is interpreted. Why am I concerned about the stretching and bending vibrations? In order to understand that, I am showing all this. So alkanes will have, you can see here octane. I have taken octane as an example. So it has only CH3, CH2, 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 finally the CH3, right? So this is a pattern for this is the IR spectrum. So what it has a stretching vibrations, which is related to CH. So many CH are there. So all the CH, which is present in CH3, which is present in CH2, they are not in same environment. So all this will give a cluster of peaks that is found between 3000 to 2800. So whereas this is because of lengthy chain. Because of the lengthy chain, these are all our bending vibrations, which are related to CH2 bending and CH3 bending, right? So this is for alkenes. So can you see the different pattern? So octane is this, whereas octene just with the additional double bond. One double bond is there, that's all. That has changed the entire pattern. So we can ignore the other things, which is similar to octane, whereas what is very important is this double bond CH stretch and C double bond C stretch. So double bond CH stretch is in little higher wave number because it is attached to double bond. So it is at 3100, whereas C double bond C is at 1600. So if I see this, I will make sure that yes, my compound is having a double bond. Next example is octane. It's just a transformation of triple bond. So can you see the difference? How octane and octane looks like? So this is related to triple bond CH and this is C triple bond C. So this area is very unique, where you will find only C triple bond C and C triple bond N. Only the triple bond will be present in this area. And this is triple bond CH. Triple bond CH has a higher frequency than the single bond CH. So it's a very interesting concept. If we feel it's boring, actually it's like cracking some, see why we are very much interested in games and other things. You crack something and you reach next level. Likewise, you should visualize this and you should try to learn and try to crack more problems so that it becomes interesting. Okay, so in this, this is just to show you that even CH stretch, if it is attached to single bond, it will have one particular wavelength. If it is attached to double bond, as we saw in alkene, as we saw in alkyne, if it is attached to triple bond, so that is sp stretch, sp hybridized, they will have a stretching vibration in different wavelengths. And aldehyde as aldehydic CH as specific 2850 and 2750. Right? These are all interesting things. So please, you can go through all this. And then this is again another way of another example, hexane. So you can see here how the CH stretch will look like, CH bend will look like. If it has more than 4 CH2 methylene, then there will be one small peak at 720 centimeter. It shows whether it is straight chain or a branched one. If it is a straight chain, you will see this peak, or if it is a branched one, you will not see that peak. So this is an example of one hexene, where this is double bond CH, this is CH, which is really associated with all this. This is C double bond C, and these are CH stretch out of plane bending, and this is also the bending vibrations. So this is for hexene, triple bond CH, C triple bond C. So all these are very interesting, and you can explore more. You can have the OH peak will be seen at 3,600, NH peak will be seen at 3,400. So I don't want to go into detail of this interpretation, not necessary also for you. But you should know the values. You should know the values. It's just a combination of each and everything. See, if it is say double bond O, it can be acid chloride, it can be ester, it can be aldehyde, it can be ketone, anything. So say double bond O peak will be there, and if it is acid, C double bond O and OH will be there. If it is aldehyde, C double bond O and this CH stretch will be there. If it is amide, C double bond O and NH stretch will be there. So it's a very interesting combination of studying all this and understanding all this and cracking what the compound is, right? Sometimes it may be given like this. See, I have a spectrum and I know the molecular formula, C3H5N. This is how many times they will give. And if you are synthesizing a compound for new, you should know what the structure is. So you have something new and you know the molecular formula. So from the IR spectrum, we can find out what the compound is. But confirmation can be made only with NMR and mass, but to some extent. So this peak is actually the aliphatic hydrogens. This is specifically C triple bond N. And there is no peaks here, so it shows that it is not an aromatic in nature. Already here also it proves aliphatic. And here this, because of this bending vibrations, this can be connected or this can be assumed that there may be one or more alkane groups can be present. So the answer is propane nitrile. Propane nitrile is the structure. See, just by seeing the molecular formula also you can say this is the structure, but you need to relate it with the IR spectrum. What is what? So at least for that you should know, yes, this is where my C triple bond N peak will be. Okay, some basic things you all should know. So now I hope you have understood the overview of the concepts of FTIR. We have seen the basic principle is nothing but it undergoes a stretching and bending vibrations. Each and every compound, it undergoes stretching and bending vibrations. And the stretching vibration occurs in different wavelength and bending vibration occurs in different wavelength. And the frequency at which the vibrations are occurring, that is explained by Hooke's law, where the wave number is directly proportional to the force constant and inversely proportional to the atoms which it is associated with, mass of the atoms, right? So depending on that, they will give, and you can also find out what the compound is, depending on the frequency at which the absorbance is seen, at which the percentage transmittance is seen, we can also find out what the compound is. It is very characteristic for a particular compound. And we have seen the instrumentation part. So it is called as FTIR, Fourier Transform Infrared Spectroscopy. We have seen what are the light sources that are used, what are the different detectors that are used, what is interferometer, because that is a unique thing which is very much associated with IR. It is not associated with any other instrument. And FT is Fourier transform, which is a mathematical calculation that converts time domain curve into a frequency domain curve. That is what we are seeing currently as IR spectrum. And IR spectrum is the spectrum that is given with wave number along x-axis and percentage transmittance along y-axis. It is divided into two regions, from fingerprint region and the functional group region. Functional group region runs from 4,000 to 1,500. fingerprint region from 1500 to 500, right? So these are some of the practice questions. I have just 10 questions with me, just to show you that this is how they'll ask in GPAT. Of course, you need a lot of revision on this so that it can be easily, you can easily qualify in analysis questions if you learn all this, right? So the first question is, methanol is a good solvent for UV but not for IR. So the reason is why it is, because it absorbs strongly in the UV region. That is the only reason why methanol is used. We don't use methanol there. We always use NaCl or KBr, right? Only those things are used in case of IR for recording the IR radiation, IR spectrum. Sorry. Right. So this is the next question. Vibrational transition existent. So from the beginning, we were studying vibrational transition. Maybe today you will remember that it is related to IR, but later there may be a confusion whether it is microwave or radio wave or X-ray. No doubt it is related to IR only, right? IR is vibrational. Vibrational is IR, right? But many compounds, it will have a combination of vibrational and rotational also. Even sometimes there may be an option, electronic, vibrational, rotational, vibrational and rotational. If such option is given, please tick vibrational and rotational. Okay, right. But if only vibrational is given, then you stick on to that alone. So what are bending vibration energy? Bending vibration energy is required. So where we have seen that? So we have seen about the stretching vibration and bending vibration, that is below 1500. That is where most of the bending vibration occurs. And that region is also called as a fingerprint region. This is a very frequent question. Functional group region and fingerprint region. Overall, it is 4000 to 1500 is functional group, 1500 to 400 is fingerprint region. So something related to region, you will definitely get one question, either in terms of stretching vibrations, more it is seen above 1500, bending vibrations are seen less than 1500. Okay, next question is whether you can differentiate the cis and trans. That is very important thing. So cis 1,2-dichloromethane is IR active, while trans 1,2-dichloromethane is IR inactive. Why? Because it is symmetrical in nature. Because we have seen that even in case of carbon dioxide also. So if it is symmetrical in nature, if you draw a line and it is symmetrical in nature, they will not respond. They are not IR active. So there we should always be clear. And cis and trans can be differentiated in such a way that there can be some peaks are seen in the higher wave number. Trans will have a higher wave number. Sorry, cis absorbs at a higher wave number than that of the trans. So that is because of the steric effect, because the two groups are in same direction. So definitely there will be a steric effect. When two groups are close, always there will be a steric effect. Remember that. This inductive effect, mesomeric effect are something associated with electron withdrawing and electron donating properties. Okay. So whenever there is a orientation, if two groups are on same side, or the orientation, when you're discussing about the orientation of the groups, definitely steric effect will come into picture, right? And they will definitely have some repulsive interaction, because in cis they are same groups, definitely they'll repel. Then next question is, how will you show that the compound under investigation is aromatic by using infrared technique? So they have given the presence of bands due to C double bond stretch in this area, and this area. So which one is correct one? The answer is C, because this is where the maximum number of aromatic bands, C double bond C stretches, occur from 1600 to 1450. This is the region from 1600 to 1450. C double bond C is seen in aromatic compounds, right? It has 3 C double bond C. That's the reason why it is of very much concern. So infrared spectra is usually plotted as percentage transmittance versus wave number. This is what is maximum it is plotted. You can also have it as percentage intensity versus wave number, but this is the correct option. You may be confused with this too. If percentage transmittance is given, that is the correct answer, right? So which of the following bending vibration takes place in different planes? So these are all, anyway, asymmetric stretching is stretching. Bending type is rocking, scissoring, and twisting. And definitely this is very frequently asked question, because there are 4 types of bending. So then there is some chances of asking questions. So D is the twisting, where it is in different planes, right? One is in plane, another one is out of plane. So twisting, you twist your leg, then that is said to be yes. The next question is, which of the following transitions mainly occur in IR? So this is what I said. You may have electronic transitions only, rotational transition, rotational and vibrational transitions, or all electronic, rotational and vibrational transition. So here the answer is B, because it's both rotational and vibrational transitions. Then last question is, the Fourier transformation is a mathematical conversion of, actually I have taken very easy questions, because I don't want you to put you down, because once you are able to answer some simple 10 questions, then you can move forward and try to learn. You will have interest and you will move forward and try to learn some more tougher questions, right? So what is the answer? It is a time domain curve to the frequency domain curve, right? So please spend some half an hour or 1 hour every day for your GPAT. Definitely you can easily score, because they are not going to ask anything beyond your syllabus. Everything is going to be within your syllabus only, and you have studied so many things. It's just a brush up, and I appreciate all the students who have attended today this session. And I thank organizers for providing me this excellent opportunity, for sharing little of what I know, and best wishes for all the GPAT aspirants. Thank you for the opportunity, and I am here to answer your questions if any doubts or questions are there.
Thank you so much, madam.
Yes, sir.
Go ahead, Kanan, if you want.
No.
Thank you very much.
Thank you very much, madam. Thank you.
Thank you, sir.
Thank you so much, madam. It is a very nice presentations. In fact, actually, this is a very tough subject, IR spectroscopy.
Those are not tough subjects, sir. It's very easy, sir.
In fact, probably maybe, madam, for us, when we were studied, no, those times and all, it is a very difficult subject, we feel. But today, it is really very simple, and you put it very nicely, ma'am.
Sir, sorry to interfere. Till now, every person in pharmacy feels analysis is the toughest subject. That's the reason I'm finding it very difficult to make the students understand. That's why I interfered and told no, sir, it's easy subject. Please make sure students are having this mindset that it is a very easiest subject.
Exactly, ma'am. That is what I'm saying. That
Yes.
before your session, we had that feeling that it is a tougher and difficult subject. But after attending your session, I thought it is really very easy, and then very easy to understand at all. So that is the reason I'm saying that it is very nice. You simply put it very nicely and very clearly explain everything, madam. Congratulations and our hearty wishes to you, ma'am.
Thank you, sir.
In fact, the energy that you have shown throughout the session is, we really appreciate it, ma'am.
In between, I lost some energy seeing the number of participants has reduced. So seeing that my energy has gone down, okay, then I thought in mind, at least those who are attending, for them I should be sincere. Then I again pulled up my energy to maximum and I tried to complete the session.
Ma'am, it's not like that. They take the PDF and your YouTube.
Okay.
They take that. They are all benefited, ma'am, but they never say.
Okay.
They're all highly benefited. Thank you.
Thank you, ma'am. Thank you.
Secondly, I would like, can I add one more thing, sir? One more chemistry.
Yes, go ahead, ma'am.
Yeah, because I'm in the industry, I've been saying chemistry is extremely important for our formulation.
Yes.
And the least importance given to pharma chemistry is really being criticized by all the organic chemists in the field, because we need chemistry to formulate. We need chemistry to, even to check the excipient compatibility. Many people in India, in India, check excipient compatibility by physical test, but actually we can do it by chemical, just initially by chemical analysis. Many people fail to, and we will be excellent formulator if we know chemistry. Because I have been at a big doctorate from Australia who was a chemistry PhD doctorate. He used to tell us the importance of chemistry in formulation, and he used to criticize our pharmacy graduates for not being good in chemistry. I was feeling very bad that time, but now I know I'm in control list. We have to do a lot of control list tablets. Formulations only with chemistry knowledge. Thank you, ma'am. Just shared.
Thank you, ma'am. I have seen your name in many of the groups. This is the first time I am meeting you. Thank you for this wonderful opportunity. Thank you.
Thank you so much. If participants, if you have any queries, once again, you can unmute and you can ask the questions directly to the speaker. Speaker is very much available and interested to address all your queries. Please ask all your doubts or any queries in the IR spectroscopy. Any questions, or if you feel shy, you can text your queries in the chat box.
Any doubt, you can type in the chat box. How was the session? Did you understand? You would have already studied if you are in final year, so it's just a brushing up.
So very clear, ma'am. Very clear and simple language you are done. Thank you.
Thank you, ma'am. Thank you.
Yes, ma'am. Generally, I think our participants are very shy. They are not asking any questions. It means that you are clearly explained everything. So since it is a Sunday, and then thanks for all your time and efforts that you have given to our GPAT aspirants. Once again, our hearty congratulations, ma'am.
There is one question in the chat box, sir.
Yeah, one question.
Yes, I'll answer that. See,
yes, ma'am. Go ahead, ma'am.
The entire IR region is 4,000 to 500. So whatever compound we record, it gives the spectrum from 4,000 to 500. So we are dividing that into two regions for our understanding. One is from 4,000 to 1,500. See, unless you divide, see, you must have seen the zigzag puzzle, right? So you divide into different things, only then you can connect them and make it into a big picture. So now the spectrum is a big picture that is given to you. So you have to divide into chunks, only then you can understand and find out what compound it is. Why we are recording the spectrum? In order to know what the compound is. So for that better understanding, we are dividing the region into two. One is from 1,500 to 500, 4,000 to 1,500. I start from left, 4,000 to 1,500. That is said to be functional group region. Why? Because most of the functional, you can find out what the functional group, what your compound is containing OH as a functional group, or amino as a functional group, or ketone as a functional group, or aldehyde as a functional group. That understanding, that knowledge you will get in that region itself, if you look at that region. So that's why it's called as functional group region. 4,000 to 1,000, it is not necessary you should see the entire spectrum. It is enough if you see from 4,000 to 1,500, if you see, you will know what is the functional group that is present in the compound. Whether my compound is having OH or NH, aldehyde, that knowledge you will get. That's the reason why it is called as functional group. Whereas 1,500 to 500, that will have many normal bending vibrations. That will not give much information about your compound. But at the same time, that region is also important because that is said to be the fingerprint region, because no two compound will have similar pattern. Even the cis and trans will have changes in the pattern in fingerprint region. So they are very unique. That's the reason why it is called as fingerprint region, 1,500 to for example, propyl alcohol, isopropyl alcohol. They're absolutely same, right? So in functional group region, OH will be present. If you are recording a IR spectrum of propyl alcohol, OH will be present. Isopropyl alcohol, OH stretch will be present. Whereas in fingerprint region, there will be slight change in propyl alcohol and isopropyl alcohol. That's the reason why it is called as fingerprint region. No two compounds will have similar spectrum, similar pattern in that particular region. But in functional group region, it will have same pattern. That is mainly to find out what functional group a compound has. Is that clear? Hope I have answered.
Yes, ma'am.
Okay, sir.
I hope that participant has understood that her question.
These two regions are in mid-IR only. We are talking everything about mid-IR. Everything is mid-IR only. Mid-IR is from 4000 centimeter inverse to 400 centimeter inverse. Everything we are talking only in terms of mid-IR only. We are not talking about far IR and near IR. We have not taken that into consideration. So far, whatever we have studied, that is only about mid-IR. Just the spectrum you are dividing into two. See, we have a body, left side and right side. Likewise, you are dividing into two. This side it is functional group. That side it is fingerprint region. That's all. For better understanding. Right? Okay.
Okay. Any more questions? Okay. So no questions. One more. No, only that is appreciation note, ma'am.
Okay, sir. Okay.
Okay. So thank you so much, madam. Once again, our
Thank you, sir.
congratulations, madam.
Thank you,
We
sir.
will wind up the show. Wishing you a very happy Sunday and happy weekend too, ma'am.
Yes, sir.
Thank you. All the participants, before we close the session, I like to announce a small announcement. That is, we are going to conduct 3 more classes until the March end. We will have a GPAT coaching classes. So we request all the participants to inform all your colleagues, to classmates, and who are all going to write GPAT. Please inform them, because so far we have conducted 14 coaching classes and remaining 3 more classes to conduct. And I think this month is very critical. So if you are prepared very well, and you will definitely will qualify in GPAT. So with this note, I request all the participants, don't miss your classes for the next 3 weeks. Okay. Meenakshi ma'am, any announcements do you want to?
Thank you very much. Thank you very much, sir.
Okay. So we'll close the session. Thank you so much for everyone. Happy Sunday. Bye.
Thank you, sir. Thank you.
Thank you. Thank you. Thank you, Mr. Kanan. Thank you, sir.
Thank you, ma'am.
Jay Kumari ma'am and Dr. Lakshmi. Mr. Kanan, thank you specially.
Thank you, madam. Thank you very much, ma'am.